Hassan's Maths channel, and I'm now going to answer question number 8, which is the final question from the June 2024 Mechanics M1 paper from International A-Level Edexcel. And here we have a question about connecting particles and inclined planes, and again some dynamics here. It says one end of a light inextensible string is attached to a particle of mass 2m. So we have a light inextensible string. Light means we can ignore its mass, and it also means that the tension throughout the string is the same all the way. Inextensible means the particles that are attached to the string will have the same acceleration. It says the string does not stretch, and the particles that are attached to it have the same magnitude of acceleration and the same magnitude of velocity. The other end of the string is attached to a particle B of mass 3m. Particle A is held at rest on a rough plane. Okay, a rough plane, of course, means we've got to deal with friction, which is inclined to the horizontal ground at an angle alpha, where tan alpha equals 5/12. So we've got to deal with trying to find the value of the angle, okay, by using like ratios, sine and cosine ratios and tan ratios, by using like triangles and trying to work out the exact value of the angles, rather than using like finding the actual angle itself. All we need is sine, cosine of the angle for us to resolve the forces. So we don't need to use the calculator to find the actual angle. We just need the sine and cosine, and we'll show you how to do that. That's a very important point. The string passes over a small smooth pulley. So it's a small smooth pulley. Smooth meaning there's no friction in it, which implies that the tension on the string on either side of the pulley will be the same, which is fixed at the top of the plane. Particle B hangs vertically below P with the string taut. The string being taut means there's tension in the string at a height h above the ground, as shown in figure 4. Then it says the part of the string between A and P lies along a line of greater slope of the plane. The two particles, the string and the pulley, all lie in the same vertical plane. So basically, if you were to look at this inclined plane from this angle over here, suppose you were looking at this from this angle over here, all right, you would see basically in front of you something that looks, if we think about it or draw it kind of three-dimensionally, okay, something that looks like this. And here would be the particle A. And what they're saying is that the particle A to the pulley and the string is going to be like, you know, the shortest distance between here. It won't be like particle A is here and there's going to be an angle, or the particle A is going to be and there's going to be an angle, and the particle B will hang vertically down such that this is a vertical triangle, completely vertical. So they're the same vertical plane. Okay, so that's what that means basically. The coefficient of friction between A and the plane is 11/36. So because, as we know, there's friction, they've told us the coefficient of friction between the plane and the particle, 11/36. So that coefficient of friction is given the symbol mu. The particle A is released from rest and begins to move up the plane. Okay, so particle A is released from rest and it accelerates up the plane, and that means B, of course, has to accelerate down the plane. Downwards towards the ground. It says, show that the frictional force acting on A as it moves up the plane is 22 mg/39. Okay, so we're going to concentrate on the particle A now. The forces acting on A are going to be its weight. Okay, it's going to be its weight, which acts vertically downwards, which in this case is 2 mg. You're going to have the tension in the string, which is pulling upwards. Okay, so that's T. Okay, and you also have the reaction force acting vertically upwards. Okay. Vertically upwards, sorry. The reaction force acts perpendicular to the plane. Okay, and the angle here is angle alpha. Okay, the angle here is angle alpha. Now, I'm going to explain why is angle alpha briefly, because some of you do ask that question, why is that alpha? Okay, if I just continue the plane down like this, just to give a bit of an idea. I'll just draw this across, and I'll make this a bit longer so that we can see clearly. Okay, before I do that, I'll just draw the rest of the forces. We also have the frictional force acting in the opposite direction to the motion. Of course, it's accelerating up the plane. So the frictional force is going to be F max. Why is it going to be F max? Because the object is moving. And we know that F max is equal to mu times R. Okay, so we want to find what F max is. So basically what we need to find is, we know mu already. Mu already is 11/36. What we need to find is what R is. Okay, so to find R, we need to resolve the forces perpendicular to the plane. Now, I mentioned, we know that this angle is alpha. Okay, now I mentioned that this angle is also alpha, but why is it alpha? Many students ask that. I'm going to quickly go through the reason why. Now, I know if I consider this triangle here, if I consider this triangle over here, let me just make this a bit smaller. Okay, you have a triangle like this big triangle. And you also have a smaller triangle, this triangle over here. Okay, so you have these two triangles, the big yellow one and the small one over here. Now this triangle over here has a right angle in this place. This triangle has a right angle in that place. Okay, this angle, this triangle has an angle alpha here. Right, now the small triangle and the big triangle both share the same angle here. That's the same angle in both triangles. So if I was to draw the small triangle out here, okay, you got a right angle and you got this angle. And if I'm to draw the big triangle out here, you have your right angle and you have this angle. These two angles are the same, right? So these two triangles are similar triangles because of angle. So if these two are triangles, this angle is alpha on this triangle, then that angle has to be alpha on that triangle as well, because they must be exactly the same, because these two angles subtracted from 180 will give you the same value in both triangles. So that's the reason why there's an alpha over here, right? Just a quick little summary for the reasons behind that. Okay, so hopefully you understood that. Okay, now I'm going to get rid of all of this stuff. Put it back again. So that's the reason, if this is alpha, this is also alpha, because of similarity. So now what we can say is, we want to resolve the forces perpendicular to the plane. So I'm going to take the R, and I'm going to take the force, the weight, and I'm going to resolve it perpendicular to the plane. So I have to go into the angle given for me to give the force perpendicular to the plane. Okay, I have to go into the angle given. So this is going to be 2 mg times cosine alpha. It's like I'm finding the adjacent side. If you think about it, if you don't kind of appreciate that explanation, you can think of this right angle triangle here. This is parallel to the plane. This is perpendicular to the plane. Parallel to the plane is opposite, so it's sine. So that force acting in this direction would be 2 mg sine alpha, which would be the weight going down, the component of the weight. And this direction is going to be 2 mg times cosine alpha, because that's like the adjacent side. So whichever way you think about it, this is going to be 2 mg cosine alpha. Now I don't need to find this component right now, because all we need to find is F max. I just need to know what R is. This will help me find what R is. I know R is equal to 2 mg times cosine alpha. Okay, the tension is acting parallel to the plane. There's no component of it perpendicular. So that's 2 mg cosine alpha. Now we want to find what cosine alpha is. We know what tan alpha is in the question. They told us that tan alpha, as they told us, is 5/12. Okay, so that we know that tan alpha is 5/12. Okay, 5 over 12. So how do I find the cosine of alpha and the sine of alpha? We need the cosine first. So how do we find that? Well, let's draw a right angle triangle. Okay, and let's say that this is alpha. And let's say that this is right angle, in which case this is going to be 5 and this is going to be 12. Tan alpha equals opposite over adjacent. So if this is 5 and this is 12, this is going to be 13. How do I know? By Pythagoras' theorem. 5 squared is 25, 12 squared is 144, 144 plus 25 is 169, the square root of 169 is 13. There are certain types of triangles which you should really have an idea of. Okay, you have 3, 4, 5 triangles. You have 5, 12, 13 triangles. You even have 7, 24, 25 triangles. There's certain Pythagorean triples, and the most common are 3, 4, 5, and 5, 12, 13, as you'll see in these questions. And that helps us get exact values for the ratios that we need. So in this case, we want the cosine of alpha. The cosine of alpha is going to be the adjacent over the hypotenuse. That's 12 over 13. And if you wanted the sine of alpha, which you probably will do later, that's going to be opposite over hypotenuse, which is 5 over 13. So you can see that straight away from here, actually. You don't have to really draw the triangle. If you recognize two of the numbers in a Pythagorean triple, you can work it out very easy. You know that you've got 5, 12, the hypotenuse will be 13. This is opposite, this is adjacent. So if that's opposite, okay, then the sine is going to be 5 over 13, because it's opposite of hypotenuse. And if this is adjacent, then the cosine will be 12 over 13, because this is adjacent side. So anyway, we know the values now of what we need. So we have 2 times mg times the cosine of alpha, which is 12 over 13. That gives me 24 mg over 13. So we want to find the frictional force acting, which I'm going to call F max. That's equal to mu, which is 11 over 36, times R, which is 24 mg over 13. Now 24 and 36, 12 goes into 24 twice, 12 goes into 36 3 times, 11 times 2 is 22, 3 times 13 is 39, so it's 22 over 39 mg, and that's what we had to show. Okay, so there's the answer to part A, completed. Now we're going to go on to part B. Okay, so part B now, question A, part B. Here we're told that we want to write down an equation of motion for B. Now, the forces acting on B are its weight acting perpendicular, so acting vertically down. Here you go, its weight acting vertically down. And you also have the tension in the string holding it up. Or, just that's attached to. So this is its weight, which is 3 mg. Now the mass is 3m, so its weight is 3 mg, and it's accelerating down towards the ground. So I'm going to resolve the forces taking down as positive. So I'll have 3 mg minus t is equal to, now remember we're looking for the resultant force is equal to mass times acceleration. So it's 3m times a, mass times acceleration. So that is the equation for motion for B. We don't have to find any values for it. All that will be found later. Okay. Part C says, show that the acceleration of A immediately after release is a third g. So we have to confirm that the acceleration of A immediately after release is a third g. So I'm going to just draw the forces, even though I've done some of them already on this diagram. So for B, we have the weight, we have the tension. Okay, tension going straight up. Okay, we already have the equation for this already. And for A, we have the tension, the weight, reaction force, frictional force. Those are the forces acting on this. Tension, reaction force, frictional force, which we call F max, and the weight, which is 2 mg. Now we already know F max from the previous question is 22 over 39 mg. Let me just confirm that. 22 mg over 39, that's what we had to show. Okay, so that's F max. Now, what we need to do is we need to consider, this is by the way 3 mg here, this is t there. So we already have one equation from the previous question, 3 mg minus t equals 3 ma. I'll call that equation 1. Now we're going to consider the particle A in order for us to get another equation of motion, which hopefully we can use then to solve the problem. So if you look at A, the forces acting on A are the tension going up, and then we have to think about the forces or resolving the forces acting on it, in this direction. We already know. Let me just change the color 1 second. In this direction, we already know, but this direction we have to calculate. Now, as I said, this angle here is alpha. In this direction is 2 mg times cosine alpha going into the angle given. Here it's going to be 2 mg times the sine of alpha. And we know that the sine of alpha is equal to 5 over 13. Okay, so now we got, for A, we got the equation of motion is accelerating up with the same acceleration as this is going down. The A's are the same, the T's are the same. Okay, so what we can say is the resultant force acting on A is T minus F max minus 2 mg times sine alpha, and that's equal to its mass, which is 2m, times its acceleration, which is A. So we want to find the acceleration. We can eliminate the tensions in these two equations. We can add these two equations together. If I add these two equations together, the T's will be eliminated. So we're going to have 3 mg, okay, minus F max, which is 22 over 39 mg. Okay, and then I'm going to also add this, which is minus 2 mg times the sine of alpha, which is times 5 over 13, is equal to 3 ma plus 2 ma, which is 5 ma. Okay, so let's simplify this a little bit. So we have, this is going to give me 10 mg over 39. So we have 3 mg minus 22 over 39 mg. We're going to have minus 10 over 13 mg is equal to 5 ma. So now we can see if we divide both sides by m, there's m in every term. The m's will cancel out. So we're going to have, let's make these all over 39. We can put this in our calculator if you want to, but if you make this over 39, you have to multiply 3, you have to multiply the top by 39. So what's 39 times 3? 39 times 3 is going to give us 117. So it's 117 over 39g minus, this is already over 39, 22 over 39g, minus, this has to be multiplied by 3, 13 times 3 is 39, that's minus 30g, equals 5a. So you have 117 minus 22 minus 30. That gives us 65 over 39 equals 5a, and the a, 5 will cancel with the 65. 13 times 5 is 65. We've got 13 over 39, and 13 goes into 39 3 times, so a is equal to 1/3 of, I've got the g here, sorry, 1/3 of g. That's what we had to show. Good. So we know the acceleration of A immediately after release is 1/3 of g. So there we have the answer to this part. Now for the final part of the question, which I'm going to do on the next page. It says, in the subsequent motion, A comes to rest before it reaches the pulley. Find in terms of h the total distance traveled by A from when it was released from rest to when it first comes to rest. So there are two parts to this journey. One part is when B falls to the ground. Okay, so A moves that same distance up the plane that B moves down. Okay, because they're connected by light in extensible string. So A is going to move the same distance that B moved. Okay, but just along the plane. So that's going to be h. Okay, so that's going to be how much it moved in situation 1 as b was falling. Okay, so that's just h. We know that height. We don't have to worry about anything else from there. Okay, in terms of finding the height there. But we will have to worry about other stuff, which I'm going to show you. Now, once it reaches this particular point, this is locked so that doesn't move around. Okay, once it reaches this particular point, okay, then what happens is there's a new situation arisen. The new situation now is that at this point, now when it reaches this point, when B hits the ground, when B has hit the ground, the situation changes. Okay, so the situation now is new. Why? Because when B hits the ground, there's no more tension in the string. So once it's got here, the string has now become slack. The tension is gone, right? Which means that the forces acting on A have now changed. They're no longer the same forces acting on A. So the acceleration of A is going to change. In fact, it's going to decelerate until it comes to rest. That's what's going to happen to it. It's going to decelerate until it comes to rest. Okay, and we got to find that small distance, which we'll call x, which is the distance we have to add to h for to find out when it comes, the distance it takes to come to rest. Okay, so we need to have a few things here. We need to know the velocity with which B hit the ground. Okay, because that's going to be the initial velocity of A in the new situation, beginning of the new situation. Because it's as if at the point at which B hits the ground, the speed with which B hits the ground is the same speed with which A is going to be at this point. And it's as if it's been projected upwards then. Because now after that, there's no tension in the string. It's as if it's just been projected upwards. And we want to see how long it takes for it to come to rest. If its initial push was this much and its final speed at this point is going to be 0 in the new situation 2. Right? So we have to consider situation 1. Okay. This situation here. And we have to consider what's happening to particle B. So this is like B is only going to be subjected to situation 1. After that, it's come to rest. So if we consider situation 1 and we consider the particle B and we consider, there's the tension in the string and everything. We consider the acceleration that it's falling down with in the initial situation. This is in situation 1. We worked out the acceleration just now. In fact, we were told to show that it's 1/3 g. So we know that it's 1/3 g, even if we couldn't calculate it for some reason. We know the acceleration as it's going down, and it's the same acceleration as this is going up until it reaches this point here. So now let's use the information we have about B as it falls down. And because it's constant acceleration, we can use the Suva equations. So S, I'm going to take down as positive because it's moving down. Okay, its initial movement is down. Okay, so S is going to be positive h. U is going to be 0. It was released from rest. V is going to be the velocity of B as it hits the ground. Now, don't think that the velocity of B when it hits the ground is going to be 0. That's not what they're talking about. They're not talking about after it hits the ground. They're talking about the speed with which it hits the ground. The speed with which it hits the ground is not the same as what's happened after it hits the ground when it will be still. You can't say that the final velocity is going to be 0. No, because that's only because the ground was there. If the ground wasn't there, it would have carried on. So we want to find the speed with which it hit the ground. That's what we mean here. And the acceleration here is positive 1/3 g because it's going down and we're taking down as positive. And the time we don't know. So we can see we need to use S, U, V, and A, sorry. So that we're going to use V squared equals U squared plus 2AS. So we want to find what V is. That's VB. So VB squared is equal to U squared, which is 0 squared plus 2 times a third G times H. Okay, H here. Things have to be in terms of H anyway. So VB squared is going to be 2/3 of GH. So I'm going to leave it as VB squared, and you'll see why in a minute. Because we're going to have to use, I think, the same formula, V squared equals U squared plus 2AS again for part B, and it will, or for section 2, and that will be something that will be useful in this format. No point working out a decimal value and 9.8 times. Just leave it like this. That's always better. Now, for the second situation now, we have a new situation. We got to first work out the acceleration of the particle A. So we're considering particle A on an inclined plane. Okay. And we have to work out its acceleration. So in this case, what are the forces acting on it? Well, you have its weight. You have, straighten up a bit. You have its weight. You have the reaction force. You have the frictional force. And there's no tension now. Okay, the tension is gone because the string is now slack. So you have the reaction force. You have the weight, which is 2 mg. And you have the frictional force, F max. Now, is F max going to be the same? Yes, because mu is the same, R is the same. So F max is still going to be the same value, which was 22/39 mg. Okay, 22/39 mg. In this case, it will stay the same. So this is going to be 22/39 mg. And then we have the component of the weight acting down the plane. Okay, which is going to be this direction here. So you're going to have the component of the weight acting down the plane, which is 2 mg times sine of alpha. Okay, so now if we consider the forces acting on the object, it's moving up. It's accelerating up the plane, and we have to find the acceleration. Okay, so this is in the new situation where there's no tension in the string now. So we got these forces acting in opposite direction to the motion. So you have minus 22/39 mg minus 2 times, remember sine alpha was what? Sine alpha was 5/13. 5/13, yes. Okay, so 2 mg times 5/13. So that's 10 mg/13. Okay, so that's minus is equal to the mass, which is 2m, times acceleration. So we can find the new acceleration now. This is minus, that's going to be 30/39. Okay, so it's minus 52/39 g. The m's will cancel out. Okay, is equal to 2a. So a is equal to 26/39. A is equal to minus 26/39 g. And 13 goes, so it's 2/3 g. So the acceleration is going to be 2/3, negative 2/3 g. So it's a deceleration, of course. So that's the new acceleration. Whoops, 2/3 of g. What am I writing there? I'm saying one thing and writing another. Negative 2/3 of g. Okay, so that's the acceleration. So now we can see the new situation. We have S, U, V, A, T. Now S is the distance it's going to move up before coming to rest, which I've called X. My diagram, I'll call that X. And U is the speed with which B hit the ground, which is going to be the square root of 2/3 of GH. I'll just write it like that. And V is going to be 0 because we want to find the time it takes, or the distance it moves until it comes to rest. It comes to rest when the velocity of a final velocity is 0. So that's the final velocity, okay, which is 0. The acceleration, as we just worked out, is negative 2/3 g, because we're taking up as positive of the plane, and t we don't know. So as I suspected, we're going to use v squared equals u squared plus 2as. Now we know what v is 0, so that's 0 equals u squared. So it's going to be basically just 2/3 gh. Okay, that is u squared. The square root of that is u, and square root of that is 2/3 gh, plus 2 times acceleration, which is minus 2/3 g, times s, which I've called x. And we've got to find what x is in terms of g. So this gives us basically 4 over 3 g times x equals 2 over 3 g times h. The g's will cancel, the 3's will cancel. So x is equal to 2 over 4 h, which is a half a h. So therefore, the total distance we need is h plus x. Okay, so the total distance moved by A, the total distance is going to be equal to h plus a half h, which is going to be 1 plus 1 over 2, which is 3 over 2 h. So there's the answer for part D of this question. And that concludes this question, and it also concludes this paper. Other questions from this particular paper can be found in the playlist, which will appear on the top right of the screen at the end of this video. Other questions from the topic of inclined planes and dynamics and forces and friction, you'll find in those playlists that you'll see there. It's also got something to do with connected particles. Okay, so you'll see some different playlists appearing, which takes you to some of those topics. I hope you understood, and I hope you enjoyed the explanations and you benefit from them. Hope to see you soon. Thank you for watching.